Welcome back. Let's continue and finish this tail latency. This is the last thing in this lecture. So remember that we are varying two parameters here, P and N, right? P is the probability that one node is going to take more than 1 second, takes forever. This is what I had at the beginning. I took a probability of 1%, and then we took 0.01% of the probability of failure. The second parameter is N, that's the number of servers, and the magic formula we are using is 1 minus P to the power of N, right? Who understands that formula, right? Okay, awesome, that's probability theory. All right, and so all I'm doing here is just using that same formula. I'm just changing the values of P and N, right? In fact, I can even do it more systematically and just doing it in this way. So what happens here? So first N, that's the x-axis. Here is the number of servers. And then the probability, yes, so the factor P is the color of the curve, right? So the blue curve right here is the probability of 0.01. This is here a probability of 0.001. And here, this one, so the green one here, probability of 0.0001. 1 in 10,000, right? So this is the factor E that I'm changing here, and this is N that I'm doing here. And basically with that formula, 1 minus P to the power of N, you get these formulas right here. And here it's actually almost a line. How do you simplify as a linear function of N, 1 minus P to the power of N? If P is very small? Anybody? 1 minus P to the power of N is almost 1 minus NP, right? And then 1 minus NP is NP. That's why it's a straight line here. And the slope of that line is actually the value P, right? It's okay if it doesn't make sense to everybody. I'm just basically doing a bit of math. But basically, this is why it's almost a straight line right here. And basically, no matter how you try to change the value of the probability here, if you find enough servers, you will always reach again a point that it's no longer negligible, right? So you will never completely bring it back to 0 because it's anyway going to be linear in P. So we have a big problem and we need to solve it, but we need to solve it with unconventional methods. We cannot just switch off the machines. We cannot just write better code. We cannot just add more resources, add more machines. On the opposite, adding more machines would make it even worse, right? So we need to find another way. It cannot even be any of that, so that you can try, you're not going to manage, right? So forget about it. But there are other techniques. And actually, again, you're so brilliant that one of you gave the solution last week or the week before. One way of doing that is to duplicate all the tasks. Every task you give to 2 slots, and then you just take whoever is finished first. That actually does a pretty good job at solving the problem, because what are the odds that both of the tasks would fail everywhere, right? So this is a good way. And then you take the first one that wins, then you kill the other slots, at least with the current task. And that's it, right? So that's actually a good way of doing that, duplicating the tasks. You can also do it in a deferred fashion, meaning that you wait for a while for a task to complete. If it's not executed within a certain amount of time, like 10 milliseconds, 100 milliseconds, just launch the same task again on another slot. So the difference with this is that here is deferred. Not at the beginning, you do 2 of them. You only launch the second one if the first one wasn't completed in a reasonable amount of time. So this is called the deferred hedge request. You can base, because how do you pick the duration that you wait until you launch it a second time? You could do it based on percentile. So what you can do is some sort of analysis of the time it takes. You basically plot some it's basically statistics, right? You run the query plenty of times, compute the time it takes for tasks to run, and do it maybe 100 times and so on, and then you get some sort of Gaussian curve, right? Well, not a Gaussian curve. It's actually going to have some fat tail, I think it's called. So it's not, but it's going to be basically a curve based on which you can compute percentiles. So you can basically pick the time so that 95% of the tasks are executed in less time than that. That would be called the 95th percentile. And so, for example, if you know that 95% of the time is going to take less than 100 milliseconds, then you can get that 100 milliseconds as the duration that you wait until you defer the request, right? Of course, you can adjust, but using percentile is a pretty good way of finding the right value to wait. And if it exceeds this percentile, you just launch a duplicate task, right? And cancel the other one. So that works actually pretty well. These are good tricks. And in fact, it was even tried with Bigtable. They did it at Google. I think they wrote a paper about that. And they tried an experience on one of their clusters, because that's nice when you're a corporation, have plenty of clusters to play with. So they sent 1,000 requests on 100 servers. They hedged after 10 milliseconds. And they plot the curve or the time it takes to compute tasks. And with deferred hedged requests, they went down from, they basically took the 99.9th percentile. It means that only 1,000th of the slots, 1 in 1,000 slots take more than that. Without deferred hedge requests, you get a full second for this percentile. But if you do the hedge request, you get that down to 74 milliseconds. So 1 in 1,000 times is going to be worse than that, but 99.9% of the time is going to be less than that. And the extra request you needed was only 2%, right? So if you had 1,000 requests, then you only needed 1,020 actual requests, because 20 of them had to be launched again. Does that make sense? And this is, for whom does that make sense? I didn't see raised hands. Okay, awesome. And this is phenomenal. I mean, here, the difference that you see, this actually works, these kind of techniques. Right? So now if you know if you work later for a large company with thousands of machines, you will know how to deal with these things. And you will, in particular, know that it will not use to improve your code if this is the problem you're having, right? Okay, and in fact, many of the systems today have that off the shelf. It's part of the configuration that you can just do it. That's the end of this lecture on performance at large scales. And I'm going to switch over to document stores. One question? No questions? All right, I'm going to move over. So let me stop the recording.